Congratulations on reaching the end of another course section. As always, let's take a few moments to review everything that we learned. In this section, we focused on structs. A struct, which is short for the word structure, is a container for related data. We use structs to model complex real-world types. Their advantage is that we can store multiple pieces of information within this larger composite type of a struct, and also have additional clarity as to what each piece of data represents compared to, for example, storing them within a tuple. So Rust has three types of structs. The most frequent one you'll encounter is the named field struct, which assigns a name to each field. A field is just a piece of data living inside the struct. It has a name, and that name corresponds to an associated value. There's also a tuple-like struct, which assigns a position or order to each field rather than a name, and finally a unit-like struct, which has no fields. Regardless of which one you are creating, you declare the struct with the struct keyword and then the name in Pascal case, capitalizing the first letter of every word. So a named field struct is the most common one you'll encounter, and when you define it, you use a pair of curly braces. It's important to note that that struct declaration defines the blueprint or template of what the struct will look like, the fields as well as their corresponding types. So the struct becomes a new type in Rust, but it doesn't have any concrete value created from it until the code specifies that. So inside the curly braces, we write the field names, then a colon, and then the associated data type that that field must store. We separate those fields with commas. So now we have a template. The next step is to actually create one or more instances of it. An instance is the realized concrete struct value. To create the instance, we write the struct name and then a pair of curly braces. We provide all of the required fields, and then this time we provide an actual value that lives up to the promised type. And the compiler will validate that you provide the correct number of fields and the correct associated types. It's important to note that the struct owns its fields and the fields own their values. All right, we also saw some shortcuts that can be helpful when you are initializing or instantiating a struct. For example, if a field matches an existing name, such as a variable or a parameter, we can simplify the field : value syntax to just field. Rust will understand that field is connected to the name in your program that matches it. You can also use the double dot syntax to copy over one struct's fields values to another struct. It's important though that that will copy everything over. So if you want to define independent values for any fields, you must declare those fields before the double dot syntax. That tells Rust to keep those field definitions, then copy over any remaining ones from the first struct. It's important to note that ownership rules apply to that double dot syntax. So if a type implements the copy trait, not a problem, because Rust will create a complete copy of it for the second struct. But if a type does not implement the copy trait, ownership will move from the first struct's field, which was the owner, to the new second assigned struct's field. The exact same field name, but in a different struct. So you have to be careful, because for any type that does not implement the copy trait, you probably want to create a clone or a manual explicit copy of that data to avoid that movement of ownership. We also talked about the debug trait. As a reminder, a trait is a contract that requires that a type supports one or more methods. By default, we cannot output our struct in either the display or debug format because it does not support either one of those traits. And what we can do is use a shortcut, which is the derive attribute. We write that on the line above the struct definition, and that automatically implements the debug trait for a struct so that we can render it in debug format, which is the format specifier, a colon, and then a question mark. And that debug string representation is just a reasonable default that the Rust team chose that's going to include the struct's name, as well as all of the fields and their corresponding values. Later on in the course, we'll learn how we can define a custom debug trait implementation so that we can customize the printed string version of a struct to be whatever we want. But usually this default derive implementation is suitable because it gives you, the developer, all of the debugging information you need when you print out the struct. Also important to note, structs by default do not implement the copy trait, so ownership principles will apply. For example, if you assign a variable holding a struct to another variable, the ownership will move to the second variable. Same principles will apply when passing in a struct to a function, for example. All right, so struct by itself is a container or a bundle of data. Where it really becomes powerful is when we can define behavior, actions, or commands that struct can respond to and execute for us. Those are called methods. A method is a function attached to a value. It is connected to, it lives inside an instance. A method, much like a regular function, can accept parameters, which represent inputs, and it can produce a single return value, which is the output. After we have our struct blueprint, we use the impl keyword, then the struct name, and then the curly braces, and inside that block, we define all of our methods. So those methods are regular functions, but one really interesting note is that they will always receive the keyword self as the first parameter. Now, what self can be can differ depending on how you write your code. Self can represent either the owned instance, the actual concrete value itself, or a reference to it. In other words, the memory address of the instance, which prevents the transfer of ownership. In addition to those two options, we have two more combinations in that we can receive either the instance or the reference mutably or immutably. If it is received mutably, that means the method body has permission to update the struct in some capacity, such as overriding an existing field's value. If it is received immutably, the method's body can read the data, access the data, but it cannot change the struct in any way. Methods must receive either the mutable struct as an owner or a mutable reference to the struct in order to have permission to modify its values. Now, there's a lot of options for how we can annotate self, so I wanted to provide them all on the screen. Here are 4 options. So the first one is immutable ownership. That means the method takes full ownership over the struct, and unless you return it at the end of the method body, that method and the self parameter going out of scope will deallocate the struct, preventing its existence and preventing any further method invocations. That's going to be the self syntax by itself, or you can provide the type of the struct, or as a reminder, the capital S keyword self. That is an alias for whatever type you are declaring the impl block for, and the advantage of that word is that it stays the same if you alter your struct's name. Therefore, the code is more resilient and adaptive to change. You can also take mutable ownership, which once again transfers ownership to the self parameter, but now the method body has permission to mutate. It's the same syntax options, except you include the mute keyword before the self keyword in the parameter list. The third option is an immutable reference. This is usually going to be preferred over ownership because you do not have to worry about return values and moving ownership of the struct to self. That syntax is slightly different. You do ampersand self, or you write self and provide the explicit type annotation as being a reference to your struct, or equivalently a reference to capital S self, which is just, again, another nickname for the same struct. Right? No technical difference, just a matter of personal preference. The fourth option is a mutable reference. That's when you want to avoid the transfer of ownership and have permission to mutate the struct, change any of its values. That means the shortcut is ampersand mute self. Notice the difference between that option versus mutable ownership on the left-hand side. It's slightly different. And so there's the kind of more verbose options where you explicitly provide the type. And then there's 4 shortcuts, self, ampersand self, and ampersand mute self, that allow the compiler to figure out which one of the 4 options you mean in any given method definition. You are welcome to define one method that does one thing and receives the struct in one way, and another method that does things totally differently. It all depends on how you want to structure your code. All right, so once we have those definitions in the impl block and we have a struct instance, we can invoke a method on it by providing the struct value, a dot, the method name, and a pair of parentheses. We need the value because a method is a function that lives on the instance. It's not available at the top level of our program like a regular function. It specifically lives inside the instance. The advantage of the method definitions is you create consistency for your own types. Your types will all support the same family of methods, so they become closer to one another in the sense that they have a reliable interface, a familiar collection of methods or behaviors that all of them are capable of executing. Methods exist to create consistency between instances of the same type made from the same blueprint. Now, in regards to the self parameter, it is required in our method definitions, but never in our invocations. Rust will provide the correct value automatically, whether it be the owned instance or a reference, whether it is immutable or mutable. Rust will do that for you automatically. Methods can define additional parameters after self if you want additional inputs to the method, and those you have to provide during invocation. You have to provide the concrete arguments for those parameters. Another cool feature is that you can invoke methods on references. Rust will dereference, which means follow that reference's address to the original struct's value in memory, and then invoke the method on the struct itself. So again, a reference to a type and the type itself are two different types. But the advantage of this design is that a method's code remains the same if your parameter is an instance or if the parameter is a reference to the instance. So if you decide tomorrow that you want to update the type of self, the code should continue to work because it's going to be handled automatically for Rust, right? This is another example of how moving towards consistency between different things allows you to write similar code, which reduces complexity. All right, an associated function is not a method. It is a function that lives within the struct's namespace or within the type's enclosure. So you cannot access this function at the top level of your program. You must provide the concrete struct and then the access syntax, which is the double dots, and then the associated function's name. And then you invoke it like any regular function. Sometimes it will accept arguments as well. The most common use case for an associated function is a constructor function, which constructs or creates a new instance of the given type. For example, we have string : new to return an empty string. Same principle applies to our own types. We usually try to live up to the consistent standards recommended by the Rust team in their own code. So we usually call our own constructor functions new as well. Not a technical requirement, but just a recommended one so that your code looks like other people's code. Finally, we talked about the other two possible structs. They are less common, but you will still encounter them from time to time. A tuple struct orders its fields by position rather than by name. So its syntax is different both in its declaration and the instantiation. We use parentheses instead of curly braces, and then we can access those fields' values with a dot and then the field's index position. A tuple struct is not interchangeable with a tuple or another tuple struct with the same fields or values in the same order of the same type, and that's the intent. The intent is that you can define multiple differing types that contain the same data in order, but distinguish between them within your program. Finally, a unit-like struct resembles a unit, an empty tuple, in that it is a struct without any data, but you can still define methods on it, and there are some use cases for this in more complex code. All right, that's all there is to cover in this section. Hopefully you enjoyed learning about structs. One thing that I like about learning about this type of subject matter is that this is the part where hopefully you start to realize how you can start to model real-world ideas in code. There's many things around us that represent a bundle of data, and maybe some of that data is numeric. Maybe some of it is text data. Maybe some of it is collection data represented by something like an array. Well, now you can gather up all of those different pieces of data and store them inside a struct, and now get closer to representing or modeling a real-world construct within your code. That's all there is to cover in this section, so I will see you in the next one.